Yes, so let's look at this closure problem with the moment expansion method. And so suppose that we can decompose the variable, the dependent variable y into the mean and the fluctuation part. And so we can expand and do the ensemble average. And so to describe the time evolution of this mean quantity, we require the knowledge of this variance. And so you see that exactly we run into the same problem as with the Navier-Stokes equation, and that stems from this nonlinear term we have with the dependent variable. And so even if the original equation was closed, that is closed in y, the averaged equation, which is that if we're interested in predicting the mean quantity, that is not closed. And so, in other words, when we're doing the Reynolds averaging, you can think of this as that we're losing information. And so, and this lost information appears then as the unclosed term in these nonlinear equations. And therefore, we end up with two unknowns, the mean y and also its higher order term, which is its variance. And so we need a closure model. In other words, we need another equation, so two equations and two unknowns, so that we can solve this problem. And of course, there are many ways to deal with this closure problem, and so different ways or different levels of simplicity. Usually, they're named after their order, and so the simplest one will be a first order closure, and so. Essentially, this is like you recognize the right-hand side is basically you're calculating the variance over the square of the mean. So this is like a coefficient of variation. And so if we use this as our simple first order model, and we can say that, let's say or the other model we add in is, the other equation we add in is a coefficient of variation. And so we now have two equations and two unknowns. So this is our closure model. And of course, this is something you say that the coefficient of variation. Yeah. So there are different methods of going about doing that. So we can assume this to be a constant, or you can assume that this is small compared to unity, such as a small perturbation. So this term goes away, and you can solve this equation. Yeah. And of course, the next level of complexity is a second order closure. And so this second order closure refers to you derive another prognostic equation for the second order moment or the second moment. And so, which is you derive another equation for this fluctuating term. Yeah. And this then, so after you do that, you end up with a new equation. And as we have seen before, another higher order, even higher order term, which is the third order moment, appear in the new prognostic equation for the variance. Yeah, so this is still unclosed. And so there are different ways, you can even go to higher order. And so you write another equation for this third order term that end up in your second order moment prognostic equation. And there are different assumptions you could make. Those are the slides prepared by Professor Kautu. And so I encourage you to take a look at these slides, but I'm just going to run across this really fast. So essentially, you end up with a mean equation, variance equation, skewness equation for the zeroth order, the first order, the second order, and the third order moments that describes the statistics of your dependent variable. Yeah, and then, assuming that you have only these three, basically these three variables and the three equations, your problem is closed. Yeah, with those assumptions applied. And so I'm not going into the details. Yeah, and so now we go to the outline of today's lecture. So any questions for the closure part? So as you learn more, you see that this closure is a theme that, as I mentioned, appears again and again in many problems. Yeah, so for today's lecture, two main tasks. We're going to look at the rough wall-bounded flow, or in the ABL context is the flows over roughness. And so
there is a question in the chat box.
Oh yeah, sure. Thank you. Is there a link to? Oh yeah, so we'll post everything after today's lecture for this introduction slides, and so you know, is the Dropbox link shareable? I guess, shall we? Is that we can make it shareable to you know, within our.
Yes, we can. Yeah, I will send the link after the.
Sure. Yeah, we'll share it with our students. Yeah, great. Okay, so the rough wall-bounded flow, yes, we'll start with revisiting the structures of the surface layer, and we'll focus on the initial sublayer introducing the so-called log law. And then we're going to zoom in a little bit at the canopy flows when you have roughness element, either in terms of vegetation or urban roughness that's present. And then we'll briefly go over the methods. I'll pay particular attention to this dimensional analysis or the similarity theory. And then I will introduce some numerical modeling and field observations and try to basically motivate the subsequent two lectures that will be led by Xiaowei and Chen Hao. And then we'll end with some big picture and to, you know, just for us to think about or ponder over the big questions. Yeah. Okay, again, those are the layers of in the ABL context. And then now you can see that this is the so-called inner coordinate, where nu over the friction velocity u star is the inner length scale. Okay, and so we have different kinds of roughness that could be present. The micrometeorology essentially focuses on the atmospheric surface layer. And that surface layer roughly matches to, in terms of, this is the inner length scale, you know, above the 30 Z plus or Y plus. And that's where both the inner equations and the outer equations apply, and the constant stress layer assumption it holds, where the wall shear stress is equal to the Reynolds stress, and the effect of viscosity within the atmospheric surface layer is negligible. Yeah. Okay. So this is another reminder. So this sketch showing various layers of a typical ABL. So I think with this concept is very important for us, you know, who study boundary layer meteorology or relevant fields. Yeah, just a reminder. Okay, so now let's take a closer look at the inertial sublayer. So if we go back here, the inertial sublayer, this is where it starts. Yeah, so it says from this picture that it roughly starts from you know, 300 wall units to 0.1, which is 10% of the total boundary layer height. And a little bit of history in the context of you know, fluid mechanics people who study this inertial sublayer. And then essentially is this realization that the Reynolds stress is constant over this region of flow, and led von Karman and Prandtl to postulate that the velocity profile is logarithmic there. And the easiest derivation you could begin with is to use an eddy viscosity concept or a first closure kind of way. And so we'll go into more detail about this first closure perspective later. Yeah, but essentially what we do is that if you recognize this is the Reynolds stress, and then in this inertial sublayer, we say that the Reynolds stress is just equal to the wall shear stress without the effect of viscosity. And with the concept of viscosity nu sub E, we can use a simple kind of Prandtl's mixing length model, if you know what I'm talking about. Yeah, but later I'll explain. Yeah. And so to essentially come up with a closure model to close this second order term, which is the Reynolds stress. And on a dimensional argument ground, we can choose this eddy viscosity nu sub e to be proportional to a velocity scale times a length scale. So the velocity scale, a natural choice, is the friction velocity, and y is usually called the distance to the wall. And this proportionality constant, as von Karman introduced, is the so-called von Karman constant, kappa. And then with this thing of the model for the eddy viscosity, we can substitute into this constant stress equation and integrate and get a profile for U. And so if we express it in the inner coordinate with the plus, you can see that this is the resulting result we get. And so this constant E is an integration constant, which encodes the information of the wall. So depending on whether the wall is smooth or rough or what kind of roughness, this integration constant will be different. And so this is the so-called logarithmic law. And of course, there have been debates about the universality of this logarithmic law. And yeah, so for example, I just want to point you to some series and recent works. This is a recent, well, not recent, I mean like 12 years ago. Yeah, so where they look at the in the experimental setting, a Reynolds number, RE tau spans, goes across a really high, high RE tau for the boundary layers. And the results support the theory of Townsend, which is, so you can read about this attached eddy hypothesis and how this could derive or lead to the logarithmic law. And also, this is a very good review paper to, if you, in your research, you want to dig deeper into this logarithmic law. Right, but essentially, it can be, or it is now, I will say, recognized that if the Reynolds number is high enough, that is, if this constant stress relation holds. Remember last time we we showed that we could derive the constant stress relation if at the high Reynolds or infinite Reynolds number limit. And so, if that holds, then the mean velocity profile as well as turbulence intensity in the inertial sublayer follows a logarithmic law. Yeah, so if you're interested, you can read up more on this. Yeah. Okay, yeah, this is just another figure showing you. So usually you will see that the people, when they want to show whether you have a constant stress layer or logarithmic layer, this is what they plot in their y-axis. Yeah, so this is to show that if you have a region that's like a constant. Yeah, so indicated by these two red dotted lines. That is an indication of the presence of a logarithmic layer. Yeah. Yeah, so now let's take a look at a closer look at this using the eddy viscosity concept, deriving the logarithmic law from a first order closure modeling point of view. And so we start with the Navier-Stokes equation. So we recognize that. And this is the viscous stress. And of course, in the inertial sublayer, this term goes to 0. And so the total shears and the total stress is constant. And this is the turbulent stress or Reynolds stress. Yeah, so again, this term originates from the advective term or the advective acceleration. Yeah. And essentially, the eddy viscosity is one of the simplest example of a first order closure to model this higher order term. And so this eddy viscosity is defined as a characteristic length scale multiplied by a velocity scale. And so to illustrate that, let's consider a stationary and a planar homogeneous flow. So that is described by a velocity scale. And so this velocity scale can choose this to be representing the velocity deficit across some specified mixing lengths. And so this velocity deficit then is proportional to some mixing lengths multiplied by the gradient of the velocity. And therefore, the eddy viscosity becomes a product of the mixing length times the this velocity scale, which is equal to the eddy viscosity squared times the velocity gradient. There's a lot of ways to choose the mixing length. And so the simplest, the simplest case is that if we just have a rigid flat wall, then this mixing length then will be given by the Kolmogorov, not Kolmogorov, the one common constant multiplied by z, where z is the distance from the boundary. If the flow is wall bounded, and of course, if you have a roughness present, then will be some adjustment to this distance to the wall. So for example, if you have roughness, like buildings, these large bluff obstacles present, then this z will not be distance to the wall, to the boundary, but it is the distance to a displaced boundary. So usually that will be, you will see that instead of z, this will be z minus d, where d is the displacement length. Yeah. And so we can simplify this equation with the assumption of the planar homogeneous flow with no subsidence and a mean pressure that is hydrostatic and at high Reynolds number. And so the equation for basically the x component reduces to this form. And so essentially with the first order closure model, applying the eddy viscosity concept, this is the equation we derive. Yeah, and so that's the equation we end up with. Yeah. And so you will see that similarly to the fluid dynamics people that derived the logarithmic law. So this is starting from a atmospheric context, without using invoking the inner coordinate, but essentially using this kind of first order closure or eddy viscosity concept. This is how we derive the logarithmic law. Yeah. So that's basically the same thing we arrive. Yeah, so there are many ways to show that whether this exists or not. So in the past, people focus on the smooth wall boundary layers, and you see that near the wall, the viscous sublayer, the viscous effect is significant, and then it's only in the inertial sublayer or the overlap region, and you have the logarithmic layer, and this shows up in the log-log plot. The semi-log plot as a straight line. Yeah, and so there are many experimental methods, and so ranging from controlled experiments and over different kinds of natural surfaces, and also like big wind tunnels and these different measurement techniques, sonic anemometers and PIVs, and to basically to investigate whether such logarithmic law exists. Yeah. And you can also essentially use the DNS and other experiments and to show that, so for example, this is plotted in the inner coordinates. So again, you see this is the velocity and this is the turbulence intensity from different experiments. So the highest Reynolds number here, so this one is from, I think it's from boundary layer, like atmospheric boundary layer experiments. And so all these are from the laboratory settings. And so there are a group of people who are, pushing the Reynolds number higher and higher in order to really see if the universality, so-called, of the logarithmic law is there, and what are the mechanisms connecting these so-called wall attached eddies eventually that gives rise to these logarithmic profile. Yeah. And of course, if you think about it, the von Karman constant, so-called constant, could also be, whether that's a constant is still also a debate. And so people conducted measurements to see what will be the von Karman constant under different kinds of flows. So this pipe flow, this is channel flow, and this is boundary layer flow.
Nature that the flow never.
Yeah. So there's like a video here showing the individual realizations and their ensembles in pipes. And so you see that, or we want to be able to recognize that, like
Nature that the flow never is reproducible in detail, no matter how.
So you see that these are showing the instantaneous so-called like velocity profile. They're never logarithmic, and it's only the ensemble averages then that will converge to this law of the wall. Yeah. And so a practical implication is that, many of you run large eddy simulations or some numerical experiments, and to try to probably, your advisor give you the first simple exercise for you to get familiar is to reproduce the law of the wall. And sometimes you do not reproduce. And that may be an indication of you're just not averaging enough. You're not collecting the enough realizations to for this statistically a valid relation to appear.
Nature that the flow never.
Yeah. Okay, so that's the log law for the inertial sublayer. And now let's try to add some complexity. So if this is smooth wall, there's nothing. So forget about these roughness, or if the roughness, they are very small, meaning that their geometric dimension is smaller than the depth of the viscous sublayer. So usually the viscous sublayer measured in inner units in the atmospheric boundary layer is about a few millimeters. And so if you have like water surfaces without significant waves, or just snow, really like smooth ice surfaces, I will say that these roughness can be considered, or the surface can be considered smooth. And so you will have a smooth wall relation. And in the meteorological context, we usually talk about the Z0 or Z0 when this is physically interpreted as a point where there is a fictitious extension of this logarithmic law that intersects with the mean velocity being 0. So that's like intersecting with this axis. And so this intersection point, which tells you something about the nature of the wall, and that comes out as a integration constant, or this in y-axis intersection. Yeah. And so physically, if the wall is smooth, then this Z0 or Z0 represents the viscous friction forces at the surface. Analogously, if you have the roughness elements that are, of course, protruding beyond or extending beyond the viscous sublayers, like in urban setting, or many other natural settings like forests or even agricultural canopies. And so we'll have these roughness elements easily extend beyond a few millimeters. And so of course, this Z0 still applies. So if there exists a logarithmic law, then you can extend this, and that the y-intercept here represents the effect of the roughness element. And so physically, that will represent the pressure or the form drag due to these roughness elements, plus the viscous friction. Because very near these surfaces, due to the no-slip boundary condition, you always have the effect of viscosity that comes into play. Yeah. And so usually for very rough surfaces we have, like in the urban settings or forests. I briefly mentioned that, but you can think of it as the wall compared to a simplest flat wall or a flat like a flat plate case we introduced for like a canonical boundary layer. So that wall is actually displaced because of the presence of many of these roughness elements. And so that's called the displacement height. And so this displacement height, usually physically, you could think of this as a distance that's determined by the, or that could be determined by the centroid position in the drag, where the drag forces act. And so this is needed when the top of the roughness element starts acting as a new surface of height, right? So we can then say that the height above the surface felt by the fluid will be Z minus D. And so you need to modify this logarithmic law. And of course, this goes back to the discussion just now for the first closure model, in the sense that when you choose the length scale for the viscosity, added viscosity, that length scale is this new distance to the wall, where your wall is displaced by the displacement height. And so there are some rule of thumb, you know, like kind of rule of thumb thing that's simple rules, basically, people in meteorology apply to estimate the roughness length and the displacement height. And so you will see that those are very convenient choices and people just apply them. However, for buildings, urban complex surfaces, does this still apply? What is the relationship? Yeah. So there's many research that goes into that. Yeah, so I will not go into details. I'm sure your advisors know this better than me. Okay. So now we talk a lot about the momentum, right? But in the ABL context or micrometeorology, urban climate context, the temperature and the humidity, they play essential roles as well. Yeah, so you can see that we can apply essentially the same first order closure to close for these second order terms for the like the heat flux, turbulent heat flux, and turbulent moisture flux. So if we do that, we can essentially derive the same similar kind of law of the wall for the scalars with respective distance or displacement height or the scalar roughness lengths. Yeah, so I'll stop here for the inertial sublayer discussions and logarithmic. So this is just a very brief introduction. Now I'm going to just spend a little bit more time on the canopy flows. Yeah, so this is like really zooming into the flows between the roughness elements. Yeah. Okay, so this is a kind of classic picture we'll get, or canonical kind of schematic. So this is the inertial sublayer. We spent some time talking about this. And below the inertial sublayer, this is called, this in general, that's called the roughness sublayer, in which the flows, they cannot be assumed to be planar or horizontally homogeneous, because they still, the effect of the roughness still felt. And so this roughness sublayer within that includes the so-called canopy sublayer. So the canopy sublayer usually refers to the airspace from the ground or from the wall to usually the top of the canopy or the mean height of the canopy, depending on your research context. Yeah, so in the inertial sublayer, we know that under neutral condition, that is when we don't consider the effect of stratifications, this is the logarithmic law. And in the roughness sublayer, but above the canopy sublayer, there are some modifications that people postulated to these logarithmic law, which I don't have time to go into the details here. But what I want to point out here is that usually in the canopy sublayer, people apply the so-called exponential wind profile. And so this exponential wind profile essentially, that has been a subject of study since the 1960s, where people first derived that for corn or maize canopy. And actually that was done in Ithaca, in the cornfield in Ithaca. And there are many previous studies, looking at whether this is really exponential or, why it is not exponential. Okay, so the question I want to postulate here is that probably many of you who work on urban canopy models know that in an urban canopy model, you need to prescribe a velocity profile that's exponential. And that exponential profile, as I mentioned, first it was derived for the vegetation or maize or corn canopy, right? But it's also applied quite widely for when urban roughness is present. Is this really a good assumption? Yeah. And so I want to give you my own take of this the contrast between a vegetation versus the urban canopy. And so if you think about the vegetation canopy, that's usually you have these trees, tree trunks, and stems and the leaves. And so these essentially, the roughness elements, they span across quite large scales. Okay, so they're, because you have the smallest drag elements that's on the size of the leaves, right? And so if you think about the drag force acted by all these collection of roughness elements of a large range of sizes, you tend to have a smoothly varying drag force distributed across the space in a forest canopy. However, when you look at the urban canopy, so of course, this is very extreme. You have these like concrete, cubicles, or not cubicles, cuboids, right? And they're displaced or distributed across. And so for the urban canopy, you see that in contrast to the vegetation or the trees, these roughness elements, they are bluff body obstacles with sharp edges. And there will be pronounced recirculations because the wind directions in these urban canopy tend to be more persistent, whereas in forest canopy, it will be more random. And so this leads to the large so-called dispersive stresses. And so this dispersive stress stems from essentially that's a spatial variation of the mean quantities. So the mean temporal average quantity deviates from essentially its spatial means. And so that's a key characteristic in the urban canopy flow. And so if we look back at the one-dimensional mean momentum equation, which, under the assumptions of stationarity and homogeneity, this is the pressure term that drives the flow, and that's the divergence of the flux term, and this is the drag force. And so it's the sum of the dispersive and the turbulent stresses. So this is the dispersive and this is the turbulent stresses in the urban canopy that matters in this equation. And this and there's a drag force. Yeah. Okay, so that's my take on the vegetation versus urban canopy, the difference, right? And so any questions here before we take a closer look at this spatial averaging concept in canopy flow, which I think is one of the most important concepts. Yeah. Do we have any questions for that?
I have two small questions. The first one is, can you go back for one or two slides? I think there is one you are showing. Yeah, this one. So the denominator of the first equation is V naught m, which is momentum roughness length.
Yeah.
Do you think I'm not sure. I'm not quite sure yet whether we should use aerodynamic roughness or momentum roughness here in
Oh,
this equation.
is it, how is that? To me, that's the same. So
Okay.
why is that different? I'm curious, like what's your view on of the
Oh,
distinction?
usually we just call aerodynamic roughness length.
Yeah,
'cause-
so so I think that's a like a terminology difference. So to me, the momentum roughness length is the same as the aerodynamic roughness length, and
see.
these things are all called aerodynamic parameters.
Parameter.
Yeah.
And the second question is about when you introduce the surface layer, I think you have two slides. The first one, you're showing surface layer is somewhere between 10% of the atmospheric boundary layer
Yeah.
to a certain distance from the actual ground surface. The one before this one. I
Oh,
think.
yeah. Okay. Yeah.
Is it?
This
Yes.
one?
So the atmospheric surface layer, the ASL, is from
Yeah.
10 to 100 meter to 3 to 5 times of the mean height.
Yes.
Yeah. But the second slide says the surface layer is from 0 to 0.1 kilometer, which is basically 10% of the ABL.
Yeah. So of course, this is highly idealized. See, there's no roughness.
Right.
Yeah.
So a more proper definition of atmospheric boundary layer.
I think
surface layer. Go ahead.
I think it all boils down to whether you are talking when you have roughness or not. So if you don't have roughness, you can say that my atmospheric surface layer starts from the ground. But when you have certain roughness, especially those large roughness that extends beyond the viscous sublayer, then you start to the effect of the roughness starts to kick in. You have these roughness sublayer. Below the roughness sublayer, you have the canopy sublayer, because usually people tend to think that in the atmospheric surface layer is where the logarithmic profile or the logarithmic law will apply, or the Monod-Bukov. Later on, we will talk about Monod-Bukov. Yeah, so where that will apply. But of course, you don't expect the logarithmic law to apply all the way to your roughness sublayer, right? Yeah. So, right. Yeah. So you don't expect this to apply to the roughness sublayer. So I don't have time to mention how you modify that, but people do modify that because this is still impacted by all the wakes produced by the roughness elements that are like mixed around this layer. And so essentially, whether this logarithmic law applies, you go back to the equation where you have all these assumptions deriving the first order closure, and you find that that will not be the case, or you need to modify that for the roughness sublayer. And of course, for the canopy sublayer, it's a different animal that you look at the equation, the drag force is there, and the dispersive stress is there. So you don't usually consider them as the surface layer, but of course everything is under the surface layer. So I don't know. Sometimes it really varies by context. So I think a term is not so important as long as you know what are the processes and the equations are there. And
then, so I asked that question is because you also brought up the figure oak kettle used in the mean logarithmic
which one? This
profile.
one?
Yeah, this one. Yeah. So in their book, they define that the surface layer contains inertial sublayer, roughness sublayer, and canopy sublayer, or like urban canopy layer.
Okay, yeah. So I think we just need the one consistent way of defining, and then remember that there are different sublayers where different equations and different processes apply because of the presence of the roughness that's going to, make the logarithmic, that first order closure we saw, that is going to deviate. Yeah.
Thank you so much.
Yeah, sure. Okay, so now I want to briefly mention this because unless you really like do research on this like a canopy flows, you know, this concept of a spatial averaging, because it's very confusing. And I myself, I got very confused about this also. So I want to show you some like really useful papers you could take a look to further, you know, understand this spatial averaging context, this spatial averaging in canopy flows. Okay, so yeah. Let me first show this picture because I think this brings up an important point for those of us who, you know, study the like cross scales. You will see that in a lot of these urban canopy models, for example, we call them like a scaleless. It doesn't matter which scale you apply, but actually I think there is a certain scale in which assumptions that go into the so-called parameterizations in the urban canopy model, you know, that apply the best. So that's at the neighborhood scale, where you could perform the spatial averaging across these box. You know, that box has a length scale at the neighborhood scale. Then you can apply many of these one-dimensional parameterizations or assumptions to represent the drag by your buildings or trees, or represent the turbulent kinetic energy and represent your energy budget. So it's this urban, this neighborhood scale. If you go further down to the micro scale, then you know, the parameterization approach may not be sufficient. You either need to really go and resolve what is going on in terms of the fluid mechanics or even radiative transfer at a micro scale. Yeah, so this is just my personal view. Yeah, we could discuss. Yeah, so anyway, so let's look at again, start from the equation. So this, all these equations and the schematic is from this paper. Yeah. Okay, so if we look at this, the equation that governs the canopy flow, you know, this is essentially what we get, and so this is buoyancy term, viscosity, and everything. So that's without any averaging. That's just the, you know, raw equation. And so essentially, when we're performing a spatial averaging, and when, you know, we're trying to develop this kind of like a spatially averaged view at the neighborhood scale. So in terms of looking at the equation, we're excluding the solid parts. So if that's a planned canopy, you take a volume average or thin slice at some height. So essentially, you're excluding all these solid parts. And so you can think of the airspace being the so-called multiply connected space. And the effect of the solid plant on the airflow can be formally described from some closure model. And so you can see that essentially, when we apply the basic equation to airflow within such plant canopy or urban canopy, there's one essential point is that we need to consider the nature of the drag forces imposed by these canopy elements. So if we just you know, blindly apply a straightforward temporal average of this equation 2, this raw equation, this does not introduce the effects of the roughness or vegetation unless you add a drag term independently as a body force to the equation. And so, however, such modification will lead to a satisfactory representation of the momentum equation. However, it does not adequately represent the effects of canopy because this is a retarding body force. So it's like you're adding a momentum sink to the equation, to the momentum equation. And so this will have the effect of suppressing the turbulence and extracting momentum from the flow. And so essentially the canopy effects will enter more satisfactorily if we consider a spatial average of the equation over the horizontal plane. So this horizontal plane as is shown in this picture. And so usually when we're considering a temporally average equation, we perform the so-called double averaging, where the spatial and the temporal average are both applied to this equation. And so usually we use a overbar to represent the temporal average and a square bracket to represent the spatial average. Okay, so if we do that, so that's the temporal average, you notice that this higher order term appears in the same thing as we're doing the Reynolds averaging. And now if we look closer at the spatial average, let the angle brackets denote the horizontal average of the flow variable. Then we usually use the double prime to denote the departure from the horizontal spatial average. And so you can write the velocity field as being made up of two parts, the spatially averaged one and its departure. And then we can perform the Reynolds average or the temporal average. And so we'll put a bar over these doubly averaged quantities. Okay, so that's where the spatial averaging concept comes in. But what I want to mention here is a very important distinction of the spatial averaging in this kind of canopy flow, which essentially it boils down to, when you're considering some of the commutation properties. So such as, so if you're considering the, let's say you're taking a spatial average over some spatial gradient, okay? And you can read all these and prove using the Green's theorem, but it essentially boils down to a general rule is that if you're considering some quantity phi here, spatially averaged, so that's a formal definition of the spatial averaging. You're averaging this across the region R, where R represents this multiply connected airspace, okay? And if this phi, this quantity is constant at the air element interfaces, so this is the multiply connected region R, and all these circles here represent the solids. And so we have an interface that's represented by these all these lines, solid lines. And so if the phi is constant at these air element interfaces, then the horizontal averaging and the spatial differentiation commute. And then, so this relation will hold. You can directly pull in the spatial averaging to your phi. Otherwise, they do not commute. Yeah. So in other words, this term is not zero. Okay. So this the spatial average of the dispersive quantity or the gradient of the dispersive quantity is not zero. If you have some, if this quantity is not a constant at the interface. Okay, so to give you an example, you can show that the pressure field varies. So these are the interfaces denoted by the dotted lines of the solid elements. So these are the pressure fields. And you see that this line indicates the horizontally averaged pressure. And all these, these quantities show the temporally averaged pressure. And so your pressure double prime or the departure or the spatial departure of pressure from its spatial mean, horizontal mean is pressure over bar double prime refers to this quantity. So you can see, of course, the pressure field is not continuous across the this air solid interface. And so, of course, the this commutation property will not hold. Yeah. And so let's look at some like general rules you remember is that, so let's say this is your continuity equation, and in compressible flows, all these quantities are zero. Yeah, so the double primes here, all these quantities are zero. However, let me ask you this question. So if now you consider, so this is a second derivative of your velocity, okay, given some kind of flows that look like this. So you have a flat plate, and this is the velocity distribution across the flat plate, and this is the gradient across the flat plate. So does this relationship hold? Yeah. No, sorry, I need to, so there's a bracket here. So the bracket over this quantity. And so from our discussion, because you have a discontinuity where this gradient is not constant across the air solid interface. And so this relationship, yeah, I need to correct that. So you have a bracket here. So this equation does not hold because this quantity, you have a discontinuity at the air solid interface. Right, so, I think this is one of the most subtle thing in when you consider doing the spatial averaging and dispersive fluxes considerations in canopy flows. Okay. Yeah. Are we all good? Yeah. Any questions for this part? Okay, so yeah, if not, let's move on to some methods here. So I'll first introduce the dimensional analysis or similitude, and then briefly introduce the numerical and experimental. Okay, so this stems from the question, like, okay, we talk about the initial sublayer with the logarithmic law, and kind of whether you write it in for the gradient or for the velocity. This is a logarithmic law. But what happens if we're considering a stratified flow? That is when the surface buoyancy comes into play. So how are we going to modify the logarithmic law in the inertial sublayer? And so the answer will be, oh, we need a new parameter describing the buoyancy. And what is that parameter? How are we going to describe that? Right. Essentially, you have some velocity or the velocity gradient. And again, the important velocity scale is the friction velocity. But now you have a buoyancy flux, B, affects the flow. Again, you have this distance to the wall. That's kind of the your length scale enters into the eddy viscosity or missing length. How does the buoyancy contribute to another new parameter? And so that question can be addressed from the point of view of dimensional analysis or the principle of similitude. Yeah, so you can read this quote. I don't need to repeat that. But this is like one of the principle of similitude. I think is like one of the most fundamental things in in helping us to think about the physics. Yeah, so as early as Galileo's prediction of a very simple question, which is how should strength vary with weight? And so think about if you are an like a weightlifting Olympic athlete, right? So depending on your weight, how does the weight or how does the strength in which you can lift the weight, vary with your basically your body weight, right? So how does your body weight determine your strength, in other words? Because you see in these like weightlifting Olympic Games, usually people are categorized into different weight categories. Why is that? So if we consider the strength as being the cross-sectional area transmitting the load, and so if let's say the body mass of a weightlifting athlete is given by its density times its volume, so with some length scale, and so therefore this is the length scale. And the strength will be the cross-sectional area transmitting the load, which is length squared or length squared. And so that's related to the mass over density with a power law of 2/3. Yeah. And so people in the literature, they compare the strength of champion weight lifters, right? So this is the strength versus their body weight. And they found this, and if you plot this in a log-log scale, and they confirm this 2/3 relation, right? And so that's an elegant confirmation of Galileo's prediction using the data of weightlifters, right? And so that is essentially the idea of a similitude, in the sense that, you know, what is the kind of the scaling between two variables. Yeah, so if you want to read more about the dimensional analysis in the context of ABL, you can read the chapter 9 of style. And so the basic idea is that if we're considering all the transport laws in boundary layer or the ABL, so these transport laws describing the turbulent flows, they must arrive at some relations among the physical variables that have the dimensions of fluid mass, length, time, temperature, or scalar concentration, right? So that's just governed by its fundamental dimensions. And these relations can be or must be derived from the Navier-Stokes equation or respective conservation equations. However, you know, these relationships may remain elusive if you directly derive from the equations. And so we need a dimensional analysis to arrive at some of those relations. And so this is the basic of that is the Buckingham's pi theorem, which I think in like a fluid mechanics class, introductory fluid mechanics class, you all learned about the Buckingham's pi theorem. So I will not go into, you know, explaining what that is. Yeah, so, but fundamentally, this helps us, this, you know, Buckingham's pi theorem or dimensional analysis helps us to think about the similitude relation or the dimensional analysis when we have the effect of surface buoyancy flux comes into play. And so the starting point of deriving that is to look at the turbulent kinetic energy equation, which again, I'm not going into the details. Please read chapter 5 in style if you're interested. And so essentially the starting point is that when we consider a turbulent kinetic energy, we can first make the equation non-dimensional. And when we make the equation non-dimensional, we end up having a production of the turbulent kinetic energy, or TKE, that is equal to the viscous dissipation of TKE. That's this term. And this law of the wall will be recovered if we do not have any buoyancy production or destruction of the TKE. And so we end up with you know, this term being 0, and therefore this term, which we recognize is you know, how we scale the basically how we first derive the logarithmic law. And so this will be 0. The right hand, the right hand side will be 1. And so the finding this finding has led the two Russian guys, Monin and Abukov, to speculate that this term with some length scale that they use to scale this buoyancy production or destruction term in the TKE equation, this length scale called L sub 0 or L. So later that's called the Abukov length scale. So that becomes a key dimensionless variable, Z over L, the Abukov length scale. That explains the departures from the near neutral state. Because if this term is 0, then you recover the law of the wall, right, under neutral condition. And so they, by examining the TKE budget, they sort of derive this new length scale where they used to essentially scale these buoyancy production or destruction term in the TKE. And so then they begin by arguing that the deviations from the law of the wall or the log law in the neutral condition in the inertial sublayer or the surface layer can be written as, so the left-hand side, instead of being equal to 1, that becomes a function, some empirical function of this new parameter or this new dimensionless variable or the new pi group that comes in. That is Z divided by the Obukhov length L. And this whole right-hand side is called phi m as a stability correction function, which is like an empirical function. And they cannot, so it cannot be derived or determined theoretically. However, we know that it must be constrained by the fact that when you do not have the effect of buoyancy, that is, this Z over L goes to 0, and this left-hand side must be equal to 1. We recover the log law under neutral condition. Yeah, so that's basically the Money-Obukhov similarity. And that becomes a theory with quote unquote. In fact, it's not a theory, it's just a sum derived from the theory of similitude. But people, all call that a Money-Obukhov similarity theory, or most. And so there have been many experimental efforts trying to determine the this correction function phi m. And so which we know that we need to recover this profile. And so people did an experiment in Kansas where it is very flat. And so all these homogeneous conditions can be applied. And then people compiled how this function varies as a function of, so this is the Kasi, which is basically, people use this to indicate Z over L 0. And so you can see that under different conditions, different empirical functions apply. Yeah. And so people, of course, repeated this in other settings, not just in Kansas, but in Minnesota. And so they found that this stability correction function was virtually the same. And so they call that a theory because you seem to recover something or discover something universal about this stability correction function. But of course, this is a big if, and people tend to be over optimistic. So as later on commented by Kaimon, right? Yeah, so with proper non-dimensionalization, all flow statistics in the surface layer can be reduced to a set of universal curves. If that happens, the world will be wonderful. We solve all the problems, and we solve the, the closure problem. So because the Money-Obukhov similarity, you can consider this as a so-called zeroth order closure. Yeah. So that's just we just scratched the surface of this Money-Obukhov similarity. Yeah, so I want to end this with some figures from the TKE budgets from the Stahl textbook. Yeah, and so of course, just now when we look at the derivation of the Money-Obukhov, we only look at the production term, the shear generation and the buoyancy generation, and how that balances with dissipation. It's as if we're assuming that other terms do not appear. Yeah, so but in fact, you can see that this transport term in the TKE budget, at least during the daytime, is also quite significant. And so a consequence or implication of that is when you have significant effect of the transport term, the validity of Money-Obukhov similarity is not it can become invalid because this transport term appears in the equation, and in our derivation of the Money-Obukhov similarity, we sort of just ignore that or assume that's negligible. Yeah. So of course, people compile the various like experimental relations, try to these empirical functions for the psi and phi. So I'm just going to leave you with a table here. There are empirical relations that people conducted careful experiments under which the assumptions where the Monod-Bukov similarity, that derivation apply, the assumptions hold, then, you apply these stability, so-called stability correction. Right. Yeah, so that's a very brief introduction of Monod-Bukov. Any questions? Okay, so now I'm just going to briefly introduce the methods. And so other methods apart from the dimensional analysis is that, let's just, solve the problem, solve the equations using numerical methods, applying the techniques of computational fluid dynamics. But across the scales of atmospheric science, it's almost the same. Usually that involves creating some mesh consisting of some grid cells, and you apply some initial conditions and the boundary conditions. And then with the known equations and the initial and the boundary conditions and the appropriate numerical methods, you just advance this equation in time and in space. Yeah, so I'm not going into the details of all these. I think Xiaowei will talk more about this. Yeah, but I want to highlight something here, especially for the atmospheric boundary layer. So there are different techniques regarding the scales of, how you are resolving the different eddy sizes, right? So remember, we talk about these eddies, and these eddies span across different scales. And in terms of its energy spectra, we have the dissipation range, the inertial range, and the energy production range. And so if your grid indicated by these small grids, they are smaller than the small eddies that are in your dissipation range, then it means that you are resolving these dissipation range eddies. And so this is called the direct numerical simulations. And you do not need to come up with closure models for this, because you're directly solving the equations. So there's no closure model needed, but you will be very careful with the numerics when that goes into approximating the partial differential equations into your numerical or algebraic equations in which you can solve. And but of course, this is computationally very expensive. And on the other hand, if you're putting your grid, larger than these dissipation range eddies, but they're smaller than the inertial range eddies. So this is the technique of large eddy simulation. And so you can think of these orange grids as performing some kind of spatial averaging of your original equation. And so if you're interested, you read the large eddy simulation literature, and formally you can show that you can apply this spatial averaging or spatial filter to the equation. And of course, whenever you apply some spatial filter or averaging, some information is lost that appears as the higher order terms. And so these higher order terms appears as terms that need to be parameterized at the so-called subgrid scale. So again, that's a closure problem. And then if you go beyond the inertial subrange, that is the so-called Reynolds average Navier-Stokes approach. So you are essentially resolving the energy production range, but you're not resolving the inertial range. So again, this is like you're applying the Reynolds average to your Navier-Stokes equation. And of course, you end up with the closure term, the higher order terms, and various models need to be applied to in order to close the equations and or the same number of equations as our unknowns. Okay, so that's a brief overview of the numerical. And now let's just look at some, experimental methods. And so this shows in a usual setting of the atmospheric boundary layers, when performing measurements, we're interested in capturing the fluxes, so which are the exchange processes or the exchange of momentum, heat, and the scalars between the surfaces, and they're mediated by the eddies of different sizes. And so the smallest scale eddies, they do not carry a lot of fluxes, but these larger scales, which are at around 1 second, they perform most of the fluxes. And so we need a sensor that is able to respond below 0.1 second in order to capture these exchanges. And so we need faster sensors to capture these surface fluxes. Yeah, and so just a little bit, mentioning the concept of a footprint. And so this important aspect of measurement is to keep track of where the spatial and temporal regions my sensor is actually feeling. And so, for example, if your sensor is placed higher up, your eddy covariance sensor is placed higher up, it is going to sense the surfaces that is further away in the upwind direction, compared to a sensor that is like placed at a lower position. And so this sensor footprint then becomes very important for you to interpret your measurement result, especially for those fluxes. Yeah, and so there are many ways where people have worked in for decades to come up with the footprint model to relate the sensor position to the so-called the source position that is basically describes or mapping the regions to where the sensor is seeing, right? And so a question for you to think about is that what are the variables important for a footprint model? Or in other words, if I know my sensor position, how do I basically quantify the set of regions which are responsible for the flux that I'm seeing with my sensor? Yeah, so I'm sure some of your advisors here, they're experts on this, and so you can ask your advisor. Yeah. So just run across a brief, like various kinds of instruments or types of sensors or measurements we have usually in the ABL context. And so we could have these tall towers with EC eddy covariance instruments installed at the different levels. And so that's one of the most common thing we could have. Or if we're really interested in the micrometeorology, the surface layer, we can have these tripods with different instruments mounted on these platforms. And if we're interested in the profiles, there's balloons or radiosondes. And we could have airborne sensors, which could give us profiles, and that is going to help us to probe the entire depth of the boundary layer. But of course, it cannot go that low. And in terms of the sensor types, it's the speed or the response time that's an important consideration, depending on if you want to just capture the mean or you are interested in capturing the turbulent perturbations or turbulent fluctuations to understand the turbulent fluxes. And also the approach, whether you're using a direct sensor that is touching or come into basically direct contact with the medium you want to measure, or if you're considering remote, so that is measurement from some distance, and you basically derive the signal, derive the quantity you're interested in from the signal, and that signal could be either actively emitted or some passive. Yeah, so I'll quickly go through these slides. So there are some slow sensors for measuring wind, wind propeller or cup anemometers. And so those are, like what some low-cost weather stations could, I guess, apply these concepts, or even a simple pitot-static tube. But to capture the turbulence, you need fast sensors, either hot wires or sonic anemometers. So they apply different kind of principles. So for example, for sonic anemometers, so you can essentially a sound signal is sending from 1 to 2 or 2 to 1. So under the influence by the wind, you can calculate using the concept of Doppler shift and derive basically the speed that causes this Doppler shift. As in for temperature measurement, there are different ways. So the simplest one will be some thermocouple, where this actually the sonic anemometers can also be used to measure temperature, because you can essentially derive this from the basically how the speed of sound and the temperature effects and what the relationships between them. Also, you could have thermal IR imaging, and of course, this gives you the most visually appealing representation of the temperature. Yeah, you could also measure temperature with very high accuracy with some semiconductor and resistance sensors. So other than temperature, we also have humidity. So the humidity measurements, you could have dew point sensors or capacitance sensors or resistive sensors to measure the humidity. A more fancy one will be the optical gas analyzer for humidity, such as LICOR. Yeah, so that can be pretty expensive, those research grade sensors. And in terms of remotely sensed ways of measuring wind, just give you an example of solar. So again, that uses the concept of, or the principle of Doppler shift, sending some signals and looking at the frequency shift to derive the wind. Yeah. And the good thing about the solar is that you could probe the profile or the height variation of the wind. And so LiDAR is a similar kind of concept. It's just that it's using a different frequency. And so radar is also similar concept, but again, that uses the radio waves. Yeah, there are other sensors, for example, for radiation or precipitation or pressure or trace gases. And so depending on your purpose of your research or what you want to study, basically you combine them into some platforms that we talk about. Yeah, there are some non-traditional kind of ways or less used, but maybe very interesting, such as these thermochromatic liquid crystals. Yeah, so essentially that relates the convective flow speed with their color. So they change color according to the flow speed. And you could even have pressure sensitive paint. Yeah. So just to give you a sense of the environmental sensing. So remember that this is like a budget that was, I would say, more than 15 years ago. And so considering the inflation and all that, so it's very expensive to perform this kind of environmental sensing, especially when you want to capture the turbulence. Yeah. And so last but not least, for those of us who are interested in sensing and monitoring the complex urban environment, what are our opportunities? So we could do distributed sensor networks. And so nowadays, the cost is has been driven down by the development of many sensors, and especially a lot of these low cost ones. And so that allows us to have spatially dense kind of sensor networks distributed in these complex environments, where the environment is so spatially heterogeneous. Yeah, just some old pictures from back in the days of Princeton. Okay, yeah, some examples. I'm sure many of you here are very familiar with these. So where are we heading? Or let's take a step back. So I like to consider this problem as a complex surfaces interaction with the atmosphere, where in the urban context, so of course within your urban grid box is many different things that's going on. So, but ultimately, when we're zooming out and looking at how this little grid is impacting the whole Earth system at a mesoscale, we're essentially considering how are the turbulent exchanges of heat momentum and water vapor is impacting or is interacting with the larger scale. Right, and so if we take a more kind of land-based focus, we basically have very sophisticated models representing these so-called boundary conditions. But if we want to take a more like a fluid perspective, we care about at this small scale, maybe how the fluid is interacting with the complex boundaries. So maybe we lose details of how to represent these boundaries at such details. And if you are even at a larger scale, looking at the atmospheric motions, this grid box made up of all these complex urban or other complex natural surfaces, they can be simplified in one way or another, because then your focus is just to look at these larger scale atmospheric motion at the global, synoptic, or mesoscale. So everything boils down to, how we represent these boundary conditions. Yeah. So that's just my personal take on this subject. And so, yeah, we are about to end for our second lecture. And so, any questions? Yeah, so sorry, I tried to cram in a lot of stuff.
I have one question, Chi.
Yeah.
About the sensors. So about the height of the sensors can touch, for example. So does the sensor usually in the surface layer, or it can be go further?
You mean the height of the surface layer?
No, I mean the sensor. I mean the how high, what's the elevation sensor can go so far?
Sensors.
Yeah, sensor. The measure. Yeah.
Measurements. It really depends, right? Yeah, it depends on your platform. So I've seen these tall towers, 200, 300 meters, and in urban measurements, people place these sensors on top of the roofs or some high buildings. Yeah, so it really depends. Chenghao, do you have any idea?
You mean the size of the footprint or the height of the tower?
Height of the tower or the measurement, usually how tall people do.
Ideally, we need to put all of EC systems within the constant flux layer, right? But most of the cases we cannot meet the requirements.
Yeah, because
yeah, sometimes
yeah,
I think he had one figure showing one rooftop tower, right? I remember there is one. Yes, this one. So if you take a look at this one, so this one is sort of problematic because it's so close to the rooftop. And if you take a further look at the bottom of this tower, there is a radiometer, the four-way radiometer. That one is actually measuring the radiative exchange between the rooftop and the atmosphere, which cannot be a good representation of the urban neighborhood, right? Yeah, that can be problematic. And also if the EC system is so close to the edge of the building rooftop, it will also, be largely influenced by turbulence created by the building, by the rooftop instead of the neighborhood scale effects.
Yeah, and in terms of the footprint of the aerodynamic, the turbulent fluxes measurement and the footprint of the radiometers, they do not overlap.
Right. And it changes a lot under different, conditions.
Yeah. So that's a lot of problems. And even though this is a very simple picture, I think every little detail you zoom into, you can think of a PhD thesis, basically.
Yeah, this is a very, very, very informative structure. So yeah, thanks.
Okay, so are we good? So we're good for today. Let me just stop the recording. Thanks, everyone.